In this video, we're going to wrap up our discussion of probability by talking about expected value. So when we talk about probability, we're talking about specific outcomes within a sample space based on our experiment. So we define our experiment, we determine all the different outcomes, which we call the sample space, and then probability allows us to discuss how likely or unlikely individual outcomes are. Now, when we talk about expected value, this is more of a big picture concept. So rather than thinking about individual outcomes in the sample space, we're analyzing the sample space as a whole. In other words, we're asking the question, based on all the different outcomes we can get and how likely all the different outcomes are, what's sort of the average, if we want to think of it as a probability related average, what's sort of the average outcome for the experiment based on how likely all the different outcomes are. So this is more of a big picture discussion of an experiment versus individual probabilities and focusing on individual events. So one thing that's going to be required if we're going to discuss expected value is that our experiment outcomes need to be numeric values. So for example, suppose our experiment was tossing 3 coins. We would care about the number of heads rather than a particular pattern. So sample spaces where we don't have numeric outcomes either cannot be considered for the purpose of expected value, or we have to find some way to assign a numeric value to the outcomes rather than just looking at them as they currently stand in the sample space. So we're looking at sample spaces where the outcomes are numbers. They have some type of numeric value. So the probability assignment, when we assign probabilities to our outcomes, we can think of that as a function, which is just a fancy word for rule, that's going to assign a probability value to each possible event. The events are going to be represented as the input for the function, which we're going to call x. So we have numeric outcomes in our sample space, and we have a rule that's assigning probabilities to all those numeric outcomes, and we call that the probability assignment. Okay, so in this situation, we have 2 major components. We're going to define them officially, and then we're going to put it in context. So the biggest deal is, do you get the context? Can you apply this in context? I'm not super worried about terminology, that kind of thing. I want you to be able to analyze the situation and think about it in terms of components. So the first component in an expected value situation is what we call the random variable. So it's kind of misleading, the term random variable. It is a variable and it isn't a variable. It's a rule that assigns a value to the outcomes in the sample space, and it's going to be represented by a capital letter, usually the letter X. So think of this as a way of taking all the values in the sample space, all the outcomes, and assigning them some type of numeric value. So the random variable just takes an outcome in the sample space and assigns it a value. Maybe they're already numeric. Maybe it's like rolling a die, and so the outcomes are already numeric. If they aren't, the random variable is then going to be used to take non-numeric outcomes in the sample space and somehow represent them in a numeric way so that we can then discuss this concept of expected value. Now from that, we also have the probability distribution of this random variable. The probability distribution is the further rule that's going to take all of these outcomes, which now have a numeric value, and it's going to assign a probability to each of those values of that random variable. So there's kind of a couple layers. We have a sample space that has particular outcomes in it, okay? The random variable is going to take all of those outcomes and label them with a number. If they aren't numeric in value, the random variable is going to somehow represent them using a number in some meaningful way. And then the probability distribution is going to assign probabilities to each of those numeric values. So sample space is numbered using the random variable, and then the random variables are assigned probabilities by the probability distribution function. So what we're really focused on is what is each numeric value, and then what is its associated probability. But we're looking at it for the whole sample space, not just for individual outcomes. We have to analyze the situation for the whole sample space. So this is not going to be the kind of problem where we can talk about drawing a hand of 5 cards and analyzing all the different possibilities. We may not be able to do anything like that because the way we have to assign values is in a lot of cases going to require us to enumerate all the possibilities. So we need to be able to enumerate all the possibilities in a sample space individually, one by one, and then assign values from there. So we're going to mainly confine ourselves to situations where we could actually make a list of what's in the sample space rather than just talking about it in general and in theory. So let's put this all into context. So consider that example that I mentioned above where we toss 3 coins and we care about the number of heads rather than the pattern of heads and tails. Okay, we want to define the original sample space, which would be the pattern that we get, what we actually see as an outcome when we flip the coin 3 times. Okay, we want the random variable represent the number of heads and the probability distribution based on how we've defined that random variable. Okay, so let's start with the sample space. The sample space is in fact the patterns that we get when we toss the 3 coins. So what sequence of outcomes do we get? That's where we want to start. Those are going to be the actual observable outcomes from the experiment of tossing 3 coins. Well, we could get all tails, we could get all heads, we can get every combination in between. And keep in mind, we're going to assume all 3 coins are different. So which coin ends up heads, which coin ends up tails gives different outcomes. So all the way from 3 tails to 3 heads and every combination in between. Okay, so this is our sample space based on the actual patterns we get, the observable outcomes from the experiment. Our random variable is then going to take all of these outcomes and it's going to assign them a numeric value just based on whatever type of quantity we're interested in. So the quantity we're interested in is in the number of heads. So the random variable is going to take each of these outcomes and assign it a numeric value based on the fact that we're interested in the number of heads. So the first outcome, all tails, there are no heads. So the value of the random variable for this particular outcome is 0. Well, what about tails, tails, heads? Well, there's only 1 head here, so the random variable assigns this outcome a value of 1 because there's only 1 head. So on and so forth for every possible combination in that sample space, all the way down to 3 heads. So again, we're looking for the number of heads. If we get heads on all 3, then the random variable is going to assign it a value of 3. Now notice not every outcome is assigned a different value. The value assigned depends on what we're interested in. So if we're interested in the number of heads, well, there's different ways we can end up with a certain number of heads. So the random variable may assign the same output value to different outcomes. That's okay. We're just focused on assigning a value to every variable. Some values may repeat, some may not. So from this value assignment, we're then describing the probabilities for each numeric value. So we can list this in a table. You can do it horizontally like this. You can do it vertically. One part of the table is going to be the values for the random variable, and then the next part is going to be the associated probabilities. So our random variable, we're going to call it capital X. Capital X is equal to lowercase x. What does that mean? Well, lowercase x is all the different values that our random variable could actually take on. So it could take on a value of 0, 1, 2, or 3 based on all the different values we assigned when we analyzed the sample space. Now, each of those values, we then have an associated probability based on our probability function. Now, we're basing the probability on how many heads did we get, and then what's the likelihood of getting that number of heads out of the different outcomes. Okay, so what's the probability that we got 0 heads? What's the probability that our variable takes on a value of 0? That's the other version of that question. Well, how many different ways are there to get a value of 0? Well, there's only one outcome in the sample space associated with a value of 0. And there's also only one way, based on that random variable, that we get a value of 0. So one way out of 8 different equally likely possibilities. So the probability assignment for 0 is going to be 1 out of 8. Now, what about the random variable value of 1? What's the probability that we have a value of 1? Well, there's 3 different outcomes that were assigned a value of 1 out of 8 different total outcomes. So 3 different equally likely values out of 8 equally likely values. So the probability of an assignment of 1 is going to be 3 out of 8. And then 2 is also going to be 3 out of 8. And 3 is going to be 1 out of 8. So the entire table essentially organizes the probability for all the different outcomes. So before we might have just asked the question, what's the probability of getting 1 head if we toss 3 coins? Well, the probability would be 3 out of 8. When we talk about a probability distribution, we have to ask that question for every possible outcome. We want to know what's the probability for every possible outcome. Now, I want you to notice something. If you were to take all of these probabilities and add them up, what would you get? 1/8 plus 3/8 plus 3/8 plus 1/8. Well, they all have the same denominator, so we could add their numerators. So 1 plus 3 plus 3 plus 1 is going to add up to 8. So 8 out of 8, which is 1. If you look at all the probabilities across the distribution and add up those probabilities, they should add up to 1. The 1 means we've represented the whole sample space. We've looked at everything within the sample space. We've assigned a probability to each, and 1 is representative of the whole sample space. In other words, the probability of choosing something in the sample space is going to be 1. You're always going to choose an outcome that comes from the sample space. These smaller probabilities are then associated with individual outcomes representing the actual outcomes in the sample space. So this is our probability distribution based on our random variable, based on our outcomes, okay? You can also represent a probability distribution using a histogram, which is a bar graph. So we represent our outcomes on the horizontal axis. We have outcomes of 0, 1, 2, and 3. You'll notice we don't put 0 in the corner like we normally would. We put 0 a little bit further over. And then the vertical axis represents our probabilities. We can either list them as fractions or as decimals. And then we draw a bar just representative of how likely any one particular outcome versus the other is. So this is just a visual representation of the same data. One benefit of a visual representation, though, is it's very clear which outcomes are very likely and which outcomes are less likely, just based on how tall the bars are. Okay, so now let's talk about expected value. So in the context of this probability distribution, we have numerical outcomes. They each have a probability. We know the whole situation. We know the whole sample space. We've assigned probabilities to everything in the sample space. Assume that's already done. We've already taken care of that. Okay, so when both outcomes and probabilities are numerical, in other words, we've made all our outcomes have some type of numerical value, then we consider expected value. What expected value represents is the outcome that is most likely on average in the long run. What does that mean? Well, it means imagine taking your experiment and running it a bunch of times. Each time you run the experiment, you'll get a different outcome. You may get some repeated outcomes. That's normal. That's to be expected. But you have different outcomes from trial to trial. Imagine running trials 1,000,000 times, doing your experiment over and over and over and over again. What expected value represents is the average outcome. In other words, if you took all the different outcomes you got from every single trial, what did you get on average? What was really likely? What was not very likely? What is going to be the average in the long run based on how likely some outcomes are versus how likely other outcomes are? Now, we're not actually running experiments. We're just looking at a probability distribution. We're analyzing in general based on theoretical probabilities how likely something is. So if we were to run an experiment 1,000,000 times, say we were to run this experiment 1,000,000 times, we would expect roughly 1/8 of the time we get 0 heads, roughly 1/8 of the time we get 3 heads, and then roughly 3/8 of the time each we get a 1 or a 2. What we're asking when we analyze expected value is based on the different numerical values we get and how likely they are, what's the average? What do we expect on average to get? That's going to be our expected value. Now, one thing we have to keep in mind that's a little bit misleading about expected value and is a little bit strange is in many cases the expected value will not represent an actual possible outcome in terms of all the different outcomes in the sample space, all the different values you could get. When you run trials, you have specific values that you can get. Well, when you calculate the expected value and you calculate the average outcome may not actually be a physical outcome that could result. The reason for that is based on how we're going to define it. But just keep in mind, sometimes the expected value, if we're saying it's the average outcome may not actually be one of the outcomes in the list. The outcomes in the list are 0, 1, 2, and 3. But when we take the expected value for this particular situation, the expected value may not be 0, 1, 2, or 3, even though those are the outcomes that are actually available to us. It may be something in between one of these values, because what we're doing is we're taking an average. Taking an average is defined based on division. And when we take numbers and we divide, we run into the possibility of creating fractions. If all of our outcomes are whole numbers and we're taking an average of whole numbers, well, the average of whole numbers is not always going to be a whole number. So sometimes our expected value is not going to be one of the possible outcomes, but it is representative of the average. If we were to look at all the lows, look at all the highs, and average it out in between based on the probabilities, then that's what we call the expected value. So we're going to assume we have our probability distribution. If we don't, we have to start there. The expected value of our random variable, in other words, on average, in the long run, the average value that our variable is going to take on, the average numerical outcome that we're going to get, is represented by this expression. So what we're going to do is we're going to take each of the values of the random variable and we're going to multiply it by its associated probability. We're going to do that for every value and every matching probability. And then we're going to sum up all of those products. So again, take the numerical value, multiply it by its probability for each pair, and then take the sum of all of those. That is a way of artificially generating sort of a weighted average. So we're averaging all of the values of the random variable, but we're averaging them with probability in mind. This is going to weight them in favor of outcomes that are more likely and less in favor of outcomes that are less likely. Okay, so let's look at an example. What is the expected value of the number of heads when tossing 3 coins? In other words, what is the expected value based on the situation we just looked like? Well, we have all our different numerical outcomes. In this case, we have 4 different possibilities. We could have a 0, a 1, a 2, or a 3. Each of those possibilities has been assigned a probability just based on all of those equally likely flips and then how likely each of those numerical assignment values is going to be. So we have probabilities of 1/8, 3/8, 3/8, and then 1/8. The expected value is going to take the numeric value for the outcome and multiply it by its probability. It's going to do that for every single numeric outcome and its matching probability. So we will have 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. Now, there's a lot going on here. How do you do this in a calculator? Well, you certainly can do that all in one line. Or if you want to break it down, you have to think about order of operations. Because notice there's a bunch of multiplications and there's a bunch of additions. Well, order of operations says you always do multiplication before you do division. So think of this fundamentally as 1, 2, 3, 4 different products. We're multiplying 4 combinations of numbers together. So if you wanted to break this down, do those 4 multiplications individually. You'll then take the results of those and you're going to add them together. So 4 products, add all of those 4 products together, and that's going to give you your expected value, which we define as E of X. So E for expected value of our random variable, which we're calling X. Now, if we want to do this in a calculator and you want to type it all in one line, that's fine. I would encourage you, though, to put parentheses around each of your products. So before you hit an addition, put parentheses around the things that you're multiplying together. So parentheses 0 times 1/8 plus parentheses 1 times 3/8 plus parentheses 2 times 3/8 plus parentheses 3 times 1/8. That expression is representative of our expected value. So I hit enter and I get 1.5. Now that's going to be the decimal version, but remember, if you want a fraction, take that, go to the math menu, arrow frac converts it to a fraction, which converts it to 3/2. So our expected value is 1.5, or if we wanted a fraction version, 3/2. What does that mean? That means if you were to toss 3 coins over and over and over and over again, and then average out all the outcomes based on which ones are really likely, which ones are not likely, this will be your average. Why does that actually make sense? Well, what does 1.5 represent? It certainly doesn't represent an actual outcome. You can't get 1.5 heads. If we're talking about the number of heads when you toss 3 coins, well, you can't get 1.5 heads. So it's not an actual outcome that you could get from running this experiment, but it represents the average if you take all the actual numerical outcomes and average them. It makes sense because it's the halfway point. This is a balanced probability distribution. Notice our matching probabilities as we go from the tails of the probability distribution towards the center. 1.5 is halfway between those inner two numerical values. So it's the halfway point. If we think of the average in a sense meaning halfway point, because this distribution is balanced, we can see it from the graph that it's well balanced, 1.5 is the halfway point. So on average, we will get a value of 1.5. Now, trial to trial, we're either going to get 0, 1, 2, or 3. But if we were to take all the trials, add them up, divide by how many trials we ran, it's going to average out in the long run to about 1.5. So that's our expected value. Okay, we're just going to look at examples from here on out. Different situations where expected value is applied. We have a lot of different applied situations where expected value can be used in context, and we're going to look at some of those situations. Now let's start with another simple example. So what is the expected value of the number of dots facing up for the roll of a single die? So we need to start with our probability distribution. That means define the sample space, think of it in terms of numeric values, and then find the probability for each of the numeric values. Well, if we're talking about rolling a die and the number of dots, our sample space is going to be 1, 2, 3, 4, 5, 6. Notice those values are already numeric, so the random variable doesn't have to do anything for us. The outcomes in the sample space are already numeric values. Well, what's the probability of each of those 6 outcomes? Well, as long as it's a fair die, any outcome is equally likely as any other. So 1 out of 6 is going to be the probability for each of those different outcomes. Each of the 6 outcomes is equally likely, so the probability for each of them is 1 out of 6. So if we want the expected value when we roll, it's going to be the long-term average based on each of the outcomes we get and how likely the outcomes are. So I'm going to take the numeric value, multiply it by its probability, and I'm going to do that for each pair of values and probabilities. So 1 times 1/6, 2 times 1/6, all the way up to 6 times 1/6. Now again, let's do that in the calculator. Remember, you can do this step by step, so if you want to do the individual products one at a time, you can do that. Or if you want to do it in one line, just make sure to be safe, you put parentheses around those products. So 1 times 1 out of 6 plus 2 times 1 out of 6 plus 3 times 1 out of 6 plus 4 times 1 out of 6 plus 5 times 1 out of 6 plus 6 times 1 out of 6. And that's going to give us 3.5, or if we convert it to a fraction, 7 over 2. So that's going to be our expected value. Now again, 3.5, is that a possible outcome? If we're saying that's the average outcome in the long run, is that an actual possible outcome? Well, again, the answer is no. We can roll a 1, a 2, a 3, a 4, a 5, a 6, but somehow 3.5 is the average outcome. It's the average roll in the long run. But again, that makes sense if you think about where 3.5 is within our numeric values. 3.5 is right there in the middle between our lower outcomes and then our higher outcomes. It's halfway in the middle. If all the outcomes are equally likely and the whole distribution is balanced, then in a perfect world, you would expect to get an average of about 3.5, about halfway. So lower numbers are balanced up by higher numbers. Everything is perfectly balanced in that perfect world so that we would get an average outcome of 3.5. Okay, now let's put this into the context of something a little bit more applied. Okay, so a spinner is numbered from 0 to 5, and each of the 6 numbers is as likely to come up as any other. A player who bets $1 on any given number wins $4 and gets their dollar back if the pointer comes to rest on their chosen number. Otherwise, the dollar bet is lost. What is the expected value of the game? Okay, well, we need to think about the outcomes in this situation. We've got a spinner, so we could think of all the different spinning outcomes, but that's not necessarily what's going on in this situation. What's going on is, again, you have to think about the experiment. The experiment is we're spinning it, but we're also choosing a number. So the experiment is we're choosing a number, and the outcome is either it lands on the number we choose or it doesn't land on the number we choose. Each of those different outcomes is associated with a dollar amount. So in this case, the numerical values are not the spinner numbers. The spinner numbers don't impact probability in this case, or they don't impact the actual outcomes. The outcomes are associated with whether or not we get the number we actually bet on, or we don't get the number we bet on, and then we have numerical values associated with that. So think of this as one of two outcomes. Either you win, which means it landed on your number, or you lose, in which case it didn't land on your number. Well, we need to think about the numerical value in either of these situations. In other words, what does it look like in terms of value to you if you win, and what does it look like in terms of value to you if you lose? Well, suppose you win. Okay, so you bet $1 on a number, and if the pointer comes to stop on your number, you win $4 and you get your dollar back. So do you win 5 because you get $4 and $1? Well, the $1 actually balances out, because remember, it was already yours, you bet it, and they just gave it back. So you're not really making that dollar, you're just not losing it. You put it on the table and you get it back. So it's still your dollar, but you didn't earn anything there. What you're earning is the $4. So in terms of a numeric value, the outcome of winning is associated with a numeric value of $4. Now, what about losing? If you lose, if it lands on any other number other than the one you bet on, you lose your dollar. So you don't get the dollar back. You put it on the table and they keep it. So your loss is associated with a negative dollar value. It's a negative dollar to you. It's a loss. So this would be considered gain. This would be considered loss. Now, each of these numeric values has an associated probability. The probability is how likely that particular outcome is. Now, we don't have to worry about which number goes which time. We're just thinking about how likely is it that it landed on the number you chose, how likely is it that it didn't land on the number you chose. Well, you have numbers from 0 to 5, so you have 6 total numbers, and you're going to choose one of them. So how many ways are there for you to win? Think about it that way. Well, there's 6 different possibilities in terms of where the spinner could land. How many of those possibilities represent you winning? Well, there's only one possible winning number, so there's only one way for you to win out of the 6 different things that the spinner could land on. So the probability of you winning is going to be 1 out of 6. There's a 1 in 6 chance that it actually lands on the number you chose because there's one winning number out of 6 total numbers. Now, what about losing? Well, there's 6 things that it could land on. 5 of them are going to be losing numbers. So the probability of losing in any situation is going to be 5 out of 6. Now again, notice that's not dependent upon which number you choose, whether you choose 0, 1, 2, 3, 4, or 5. It's just dependent on how many numbers win and how many numbers lose. 1 number out of 6 is a winning number, and then 5 numbers out of 6 are a losing number. So 1/6 of the time, in theory, you win, and then 5/6 of the time, in theory, you lose. Assuming you were to just bet on the same number, 1/6 of the time you win, 5/6 of the time you lose. Okay, so this is our probability distribution. Here's our numeric values, they're dollar amounts, and then these are the associated probabilities for winning and losing. So the expected value of the game is going to take the dollar amount and multiply it by the probability, and then sum up those two products for each of those different situations. So let's start in the calculator. So we have $4 times 1/6 plus -1. Make sure to put the negative. Now remember, you're not going to use the subtract button. You're going to use the negative button right under your 3. So -1 times 5 out of 6. And that comes out to a negative number. Notice it is negative. Now, if we're talking about money, in general, money is rounded to 2 decimal places. So if we round that to 2 decimal places, that's roughly -0.17 or 17 cents. What does that mean? Well, if we're thinking in terms of winning value and losing value, your gain, your loss, on average per game, you're losing about 17 cents. Now again, how does this actually work? You can't lose 17 cents. You either win $4 or you lose $1. Well, based on how likely it is to win and how likely it is to lose, if you were to look at all your wins and losses and average everything out, it averages out to you losing about 17 cents a game. So you can't actually lose that exact amount, but that is your average loss per game in the long run. Now that also means this is not a good game to play overall. It's structured so that it doesn't favor you. Most games like this where you have to make a bet and you can potentially win something do not favor the player in the long run. Yes, from time to time you will win, and there is a probability that you do win, but the games are structured so that in the long run, the player doesn't win and the house will always come out positive. Okay, let's look at a couple more examples. So maybe we can do something with cards. Let's see if we can be creative here. So a 5-card hand is dealt from a standard 52-card deck. If the hand contains at least 1 diamond, you win $10. Otherwise, you lose $4. What is the expected value of the game? Okay, so we're gonna have to be careful here. We're gonna have to be a little bit creative. Now let's think about it kind of the way we thought about that spinner game. Think about the outcomes. Well, if it's a game, the outcomes are either you win or you lose. Here, there's no spectrum of winning and losing. You either win or you lose. Now, this doesn't say anything about betting. It just says you win a value or you lose a value. So if you win $10. So winning is represented by a numeric value of $10. And if you lose $4. So that's going to be -$4. Now, where it becomes a little bit challenging is once we get to the probability. So we need to go back to actual sample space, experiment, all of that. Think about the events in question. What event represents a win and what event represents a loss? Okay. Well, when we're looking at the sample space, we're talking about 5-card hands. Okay, so the sample space for this experiment is all the different 5-card hands that you can be dealt. We've seen this sample space quite a bit. We know how to count this. We're counting the number of elements in the sample space. So there's 52 to choose from, and we're choosing 5 out of that. So 52 combination 5 is going to be 2,598,960. So that's the number of ways to get a hand of 5 cards. Now, what are we interested in? We're interested in winning versus losing. Well, we win if we have at least 1 diamond, okay? Here's the problem though. At least one diamond means we could have one diamond, we could have two diamonds, we could have three diamonds, or four or five. If we were to directly calculate the probability of having at least one diamond, we have to analyze the count in all five of those situations. So you'd have to count how many ways there is to have one diamond and four other cards. Count how many ways there are to have two diamonds and three other cards. So on and so forth for all those possibilities. But if you remember, we can also calculate this kind of probability using the complement. So if an event in question is relatively complicated to calculate the probability for, but the complement, the opposite event, the other set of outcomes is easier to calculate the probability for, then we can calculate that probability. Now, when we're talking about probabilities and complements, we're really just talking about a count right now, because keep in mind, as long as the experiment is the same, the sample space is the same, so the denominator for every probability is the same. So what we're really looking at is counting outcomes, counting possibilities. Well, what do the complementary outcomes look like in this situation? Because clearly the outcomes for the actual event representative of winning could go a bunch of different ways, and counting there might be a little bit more complicated. Well, if winning means you have at least one diamond, the opposite of having at least one diamond is no diamonds at all. So winning if you have at least one diamond, losing if the opposite is the case, losing if you have no diamonds. Well, no diamonds can only look one way. It just means you don't have any diamonds. There's no specific combination about other cards that we're interested in. All we're interested in is the fact that you don't have any diamonds in your hand. Winning would be 1 and 4, or 2 and 3, or 3 and 2, a bunch of different combinations. No diamonds just means no diamonds. It means we chose from the portion of the deck that didn't have any diamonds in it. So that means, imagine taking the deck of 52 cards and throwing away all the diamonds. Well, how many cards are left? We have 39 cards left that represent the whole deck with no diamonds in it. But we're choosing 5 cards from that. So 39, combination 5, which comes out to 575,757. That's going to be the number of hands that have no diamonds. Another way of thinking of it is that's going to be the number of hands you could receive that represent you losing. If you get any one of these hands of cards, it's not going to contain a diamond, so you would lose the game. Well, if there's this many hands you could get in total, and this many won't have any diamonds, then the rest of them do have diamonds. They do have at least one diamond. So this is the complementary event. This is the losing event. This is the count for the winning event, the opposite count. So if this many hands have 5 cards in total and this many have no diamonds, then if we subtract, that's going to be the remaining hands, which represent hands that have at least one diamond. Those would be winning hands. So this is the number of losing hands. This is the number of winning hands. Automatically, just comparing those two counts right there, this looks like a good game to play. There are more ways to win than there are to lose, which means it benefits the player. This particular game is going to benefit the player. But how does it benefit the player? What's the actual value? That's where our probabilities come into play. So what's the probability of winning? Well, this many 5-card hands are going to win out of the total possibility. So I take my number of ways to win divided by the total number of possibilities, and that's going to give me my probability for winning. To 4 decimal places, that comes out to about 0.7785. Now, what's the probability of losing? You can actually calculate this a couple different ways. So you can calculate using the count divided by the total number of possibilities, or you can go one step further with that complement idea. So if you know this is the probability of one event, then the probability of the complementary event is always just 1 minus this probability. So either way, either taking the ratio of losing hands out of the total number of hands, or 1 minus the probability to get the probability of the complement, will give you this particular probability. Notice again, those probabilities are going to sum to 1, not a coincidence, because an event and its complement, those probabilities are always going to sum to 1. So the probability is the hard part here. Once we know the probability, the expected value formula is routine and we always apply it the same way. So $10 times that probability, and then negative $4 times that probability. So if we want to do that in the calculator, okay, we have 10 times 0.7785 plus negative 4 times 0.2215. And that's going to give us about $6.90. There's a bad glare. There we go. About $6.90. Okay. Now again, put it in context. You cannot actually win this amount per game. You either win $10 or you lose $4. But if you were to play the game a bunch of times, take all your wins, take all your losses, and average it out to an average amount per game, this is going to be the average amount per game. Because that average is a positive number, that means this is a good game to play. It means it's a game that in the long run will favor you. Yes, you will win some, yes, you will lose some, but in average, a player comes out positive in a game like this. So this would be a good game to play versus the last one, which in general was not. Okay, let's look at one final example. You're interested in insuring a car audio system for $2,000 against theft. In other words, if it's stolen, they'll give you $2,000. An insurance company charges a premium of $225 for coverage for 1 year, claiming an empirically determined probability of 0.1 that the system will be stolen sometime during the year. What is your expected return from the insurance company if you take out this insurance? In other words, do you expect for this policy to actually be worth it? How do you know if it's worth it? What are your two outcomes here? Well, either it's stolen and you get money from your policy, or it's not stolen and you don't actually get any money from your policy. In either situation, you have to pay for the policy. But if it's stolen, you get a payout. If your audio system is never stolen, you don't get a payout. So the two outcomes here are either stolen or not stolen, and then the numeric values that go with those. So suppose your audio system is stolen. Suppose there is a theft. Let's think about what would happen. If there is a theft, the policy insures you for $2,000. So in other words, the insurance company will give you $2,000. But do you really come out $2,000 positive? The answer is no, because you have to pay the premium. In order to be eligible for the benefits, you have to pay the premium of $225. You pay that no matter what, whether you actually get any money from the policy or not, you have to pay that $225. So in terms of the actual gain to you, it's the difference between the two. You made $2,000, but if you account for the $225 you already paid, then you're really getting $1,775 out of the deal. You're getting the difference between the two. Now, what's the other possibility? The other possibility is that it's not stolen. There's no theft. Well, if there's no theft, then you're not getting $2,000. If there's no theft, then you don't have to cash in on the policy. But you don't break even, because remember, you had to pay the premium. An insurance policy is a gamble. You're gambling, am I going to need this? Am I not going to need this? If I don't have it, well, I wish that I did. That kind of thing. So you have to pay the $225 premium even if nothing happens and you never get the $2,000. So the numeric value of no theft is actually a negative value. It's negative $225. But those are the only two possibilities. They don't have intermediate payouts depending on what happens. We're just assuming either the system is stolen or it's not. So either you get the money from the policy or you don't have to make a claim and get the money for the policy. Now we need to know the probability in each situation. So the insurance company is basing their rates and basing their payout on how likely it is that your system is going to be stolen. So empirically determined probability just means they've based their probability on past results from previous customers. How likely was it that customers would have to make a claim during the year? They determine the probability, they determine how they're going to charge you based on what they've seen from past customers. So they determine with a probability of 0.1 that your system is going to be stolen just based on what they've seen in the past. Well, if it is stolen, remember that's where you actually benefit from the policy. So you get the 1775 at a probability of 0.1, just based on what the insurance company is saying. That's the likelihood that this will be the outcome and this will be the gain to you. Well, if that's the probability of it being stolen, what's the probability of it not being stolen? Well, think of those as complementary events. Stolen versus not stolen, those are opposite complementary events. So if the probability that it is stolen is 0.1, then the probability that it is not stolen is going to be 1 minus that value, which comes out to 0.9. So 10% of the time, if you want to think of it this way, 10% of the time, your policy will make you $1,775. Of course, you have to lose your audio system, but you'll have this value from your insurance policy. 90% of the time, all you're going to do is pay your premium and lose your premium, and you're not going to see any money from the policy because it wasn't stolen, so you didn't have to make a claim. So what's the actual long-term value of the policy? What's the expected value? What do you actually expect to get out of this in the long run based on how likely one outcome versus the other is? Well, again, you're going to take the numeric value, multiply it by the probability. So let's do that. So 1775 times 0.1, that would be if you actually use the policy, think of that as a win in a sense, plus negative 225 times 0.9. And that's going to come out to negative 25. Now we're talking dollars here, so that's negative $25. That is the expected return on this policy. Now, in this situation, it's a little bit more complicated to analyze what this means. But think about it from the insurance company's standpoint, or even from the standpoint of a bunch of customers. If a bunch of customers took out this particular policy, say 1 million customers took out this policy, and you looked at all of those customers who actually had to make a claim, who didn't have to make a claim, we know that everyone who made a claim got $2,000 and came out $1,775 in terms of gain. And everyone who didn't have to make a claim lost the $225 premium. If you were to look at all the different customers that took out this policy and either did or did not make a claim, and you averaged out the value, either the gain per customer or the loss per customer, this would be what all of that averages out to. It averages out to about negative $25 per customer. Now, what does that mean for you? That is the expected value for you. It means on average, you'll lose $25 from this particular policy, just based on repeated analysis of what would happen from customer to customer, year to year, claim to claim. On average, you lose $25. That means that they've specifically set the premium value with these probabilities in mind. They've set the premium value so that on average, they will make $25 and you will lose $25. Now again, from customer to customer, some customers will get a payout and some won't. Some they'll just get to keep the premium for. But on average, this will be the average amount that the company makes and that you lose for this particular kind of policy as described. So these are just a few examples of situations where you can apply expected value. Expected value is used in a lot of business analysis situations. If you want to analyze gain in a particular situation versus loss, based on all your different outcomes, the likelihood of each outcome, this is a tool that you can use to analyze those kinds of situations.